Okay, so the last, is it 45 minutes now, right? We can do it. Eigenvalue problems. Right. So the general problems, sorry, the general properties of problems in matrix form, right? Finding eigenvalues, finding eigenvectors, should be remembered. There can be help to find mistakes. There can be help to select the right algorithm for your problem. So if you have a Hermitian matrix or you have a real valued symmetric matrix, you can use fast specialized algorithms as they're given by LAPACK, for example, to solve or to find your eigenvalues and eigenvectors. Now, what else can we do here? Right. I think that's it already, right? We get eigenvalues, we get eigenvectors. That's what we wanted to have. Then we check if our A times eigenvector times A times eigenvector equals lambda times eigenvector, because they should be the same on both sides of the equations. We did this, I think, here, right? A dot eigenvector times lambda. Good, it seems to work. Now we can go already to the next problem. And so it's getting more and more interesting in terms of problems that could be solved, as well as the advantages of a computer helping us solving these issues. So we're going next to look into non-linear problems. Do you remember what is a linear problem? So linear problems are where your solution elements are written to the power of 1. Now, in non-linear problems, we have other functions. For example, the root of a function. We already met our x square minus tangens hyperbolicus. Where is it? Here's something similar, x plus tangens x, right? So problems that are not to the power of 1 in our for the required relation between input and output. So first, we're looking into univariant nonlinear equations. So univariant is just one variable, x. If we have more than one, we call that multivariant, right, for many variables. Let me check the stream. Stream is on or not? Here it is on. Yeah. YouTube does not receive enough data. Yes, what should I do? Connected, right? Yes. Well, I can just continue and then hopefully the stream is not affected for those who watch at home. But now examples of univariant nonlinear equations are given here. For example, x squared plus x minus 1. We solved that equation. We solved equations of that form before, typically quadratic equations. And we know some SymPy can do very well with them. Then we have here x cubed minus 2 sine x, or x e to the power of x minus 2. When we're looking for the roots of these univariant functions, we have options now, right? We can have SymPy, we can ask for help in NumPy, or we can ask for help in SciPy. Here in this example, we look into SymPy. We have a quadratic equation, and we execute. Let's see. We will find the PQ formula. Right? This is basically an example we had before. So it should be the ABC formula. It takes a while. Meanwhile, We move on. Now something more advanced, a cos minus b cosine. We would define the problem, ask for a solution, and SymPy provides us some solution. Very good. So SymPy can handle a little bit of this. Now we ask x minus, ax plus b tangents x, and we again would ask SymPy for a solution, but that time SymPy cannot find a solution, and we already know the reason. Nobody implemented the algorithm to find the solution. So we go up because the computer is finally done. Here we see the A-B formula. Then we have, wait a little bit for the second solution, and the third solution we revise last. Right, so then the last equation has no solution from SymPy because nobody implemented the algebraic solution. Well, or any solution among which the algebraic solution is actually not available. So the second solution is now here, right? And the computer now works on the third solution, which still takes time. And you see this here in the little star that indicates a running code block. So if we cannot find a solution through SymPy, we can actually use matplotlib to find a solution. Sounds crazy, but it's possible because we call this finding a solution by plotting. It's a simple solution, but don't disregard simple solutions. So here the example. We are defining our function f1, that is x minus tangents hyperbolicus. We have a second function that is sine of something that depends on x minus x squared. There also we would have trouble finding a solution. Next, we asked matplotlib its subplot routine to give us two x's in one figure. And then in one figure, we're going to plot function 1. And in the other one, we plot function 2. And it looks like this. So the plots are not the most advanced plots, but we can apply our knowledge of solving functions, which is basically finding the root of the function. And the root of a simple function is just the intersection of a function with the x-axis. So I look at this function and I see how many intersections now. f1 has how many intersections in this plot? Very careful, it's a trick question. No? So if you just use your eyes and not your brain, you see 3 intersections, right? 1, 2, 3. But do you remember what is the form of a tangents? So the tangents you normally start drawing at 0, right? And then it's flat for a while and it goes to infinity. At like, what was it? Pi half, right? And it goes to minus infinity at the other part, minus pi half. So far, so good? Yes? Remember, here we have minus tangents. So I can cut this. Now it's just a function tangents of x, right? And I want to, I plot. Yes, there we go. So here is my tangents. Right? So we see something goes to infinity, to larger values, and minus infinity, smaller values. We have the periodic images here and there, but then there's this weird part in between, right? This straight line that goes straight up or straight down, depending where you see it. Then you must remember, hey, I'm actually using, what am I using here? NumPy. So I get a regularly spaced grid. And then to plot, I'm using plot, right? And we said plot just connects the data points. That means the last point that is very close to, like pi half, right, gets a very large value, and the next value is actually very, very small. And then Python in plot connects these points, and that gives you the straight line. If you want to remove that, you do scatter here, okay? Zoom out a little bit. There we go. You see? So that funny straight line is gone because there are no data points actually. It's a plotting artifact. So one more time, how many intersections do you see here? Here is one, right? So far, so good. Now we go back to our original problem, f of f1 equals minus tangents. And there we go. There should be only one, right? But now our plot is very thick. So what do we do? How do we fix this? Still very thick. What is the attribute we can change? Marker size, right? Is it? It's taking a long time, which is normally like, oh, you did something wrong. There should be something called marker size. Wasn't it marker size? Was it size? Anybody remembers? What is the attribute? Plotting? I apparently don't remember. Which is okay. Because I still remember how to plot. And then I get a weird line, but I can use my brain to say, huh? What? Line with 0.2, yes, that's too small. Right. So that we have, here we go. These lines here, the straight lines going up, down, are artifacts through plotting. So we only have one intersection over here. Right? So the root here is somewhere 0. There are, of course, if you extend the plotting space, then more intersections. Let's see. Plotting, let's go to 6. Yes. So right, so we have here our real function, artifact, real function, and somewhere here is the next intersection, right? Artifact. And when we extend this a little bit further, let's go up 9, we actually would notice that the intervals between this intersection, the next intersection become larger as through the shift of x, right? So it's x minus tangent hyperbolicus. So you basically shift your tangent hyperbolicus up with each period and slant it a little bit. Okay, so but in principle we could now read the values of the root, our solutions from this plot. It's getting more, maybe not more insightful, but more valuable to use a computer to do this when you see this plot here, right? So here we have many roots, and it's quite hard to plot this by hand and then read off values accurately. So remember, everywhere where the function crosses the x-axis is a solution, right? The root. Right. So the next example is square root x tangens hyperbolicus. Because what you would do in practice, let me try to scroll down. No, cannot. Here is right, really to try to read off solutions. On this plot, we have two functions: the square root of x, that is here the bluish dotted curve. We have the tangens hyperbolicus, still again with the artifacts, and then possible roots. Now, when we see already, right, zoom in very closely, it actually looks like we have a slight mismatch here. So then in the code block, we actually, right, see, okay, here's the plot preparation, we have the function definition, we have the tangents of x, then we plot these parts, or we have the square root of x over here, right, and we put a vertical line here. The vertical line is here at 2.1. We shift it a little bit to the right. Try again. Maybe 2.2 to see what the black curve is doing. A little bit too large, so I go to 1.19, 2.19. Yes, this is a pretty good solution now. You see that? So I really want to hit this point where the square root hits the tangents and put my vertical line through it, the dashed line here. So I now graphically changed the solution. And remember, so what I did is basically I started at 2, maybe, because 2 looks all right. Oh, it's a little bit too far to the right, too far to the left. So I go 2.3. A little bit too far to the right, so I get 1.15. Maybe too much to the left, and so I change step by step until I get a really, really good solution. Now, this gives me a very, very good idea. Why don't I use Python to do this for me? Because I can just start guessing a solution and then switch more and more close to my real solution. And I know it's my real solution because I can measure the function values. And if they are almost identical, I have found my solution. Let's implement this, and let's call this the bisection method. Now, this is a very, very easy to implement method. The idea is given here. Look at that. So we have a very, very special function. Could be any function. And what we want to have is the root. How many roots are given here in this example? 1. Where is the root? Where the red line is. So, what do I need now for the bisection method? Well, I need to choose a value somewhere. I choose, for example, a. Oh, I see a function value, right? F of a would be here, some value negative. Then I choose a value quite far away from a. Let's be that c. Now, when I check the function value of c, I know, hey, c is the function value of f of c is positive. But this is now very, very interesting. Because when I start somewhere, it's negative, and then I go somewhere else, it's positive. I know I must have gone through 0 somewhere. It's like when you go from here home. Inside, it's not raining. But when you reach home, you're all wet. Then I know outside it was raining, right? Kind of, right? So the crossing from plus to minus somewhere is 0 in between. Very good. So what could have happened is instead of choosing A in the beginning, I could have chosen B, right? And B and C are both positive values. That means I'm not sure if there's a minus in between or if I have a root. Then I can do two things. I either choose a smaller part to hope there's a value that crosses to 0 that I don't see, or I choose a larger distance from C, right? But I really want to have somewhere a change of sign at the beginning. Because when I choose A and C, I know that there is no crossing through 0 between B and C. But there is a crossing because B is also positive between A and B. Right? So I start with two intervals, two values. I find my change of sign. I separate these two intervals now in half. Then I check again, or is there a change of sign in interval 2 that is spanned from B to C, or in interval 1, which is from A to B. And because I knew before I had a crossing through 0, and it is not between B and C, therefore it must be between A and B. But then I'm going to change to analyze now the interval between A and B. I again say, okay, A, B, and C. I'll start with a smaller interval. I know I do have the change of sign somewhere, but I put in intermediate value, well, in the middle, somewhere between the new interval. Right? That is again B, and I check again, where is my value change? And that would be here again in the second interval. Okay, and I do this over and over again, and what I find in the end are smaller and smaller intervals. Right? So I reduce the big space to smaller and smaller regions. It always will be, or your values between A and B somewhere, but the range is much smaller. Okay, so this algorithm has basically three parts to it. Start interval, you must select A and B, start and stop. Get the function values from A and B and check if those values have different signs. Second, evaluate the function in the middle of A and B. That will be point M. And when the sign of the function is different between f of A and M, then start from 1 with A, B equal M. So you go back here, right? If the function value changes sign, of course, between f, B, and M, then you use that interval. So the bisection method searches for a sign change in an interval and reduces the size of the interval iteratively. And something similar I actually did here, right? I checked how much was I away from my solution, either being above or below that crossing. So, do you understand the algorithm? Okay. So now we implement, right? And let me first show you the end result of what we get. We start with a rather simple equation that looks like some form of exponential function. We have a start and stop interval. and then we have an intermediate point M1, M2, M3, M4, M5, and there's an accumulation of points over here, right? Because the intervals become smaller and smaller. Okay, let's look into the code. Right, so we import numpy and matplotlib, and then we say our function that we don't know, but we do know, is the exponential function shifted down by 2 units. We define a tolerance that gives us the accuracy that we want to have, a start and stop interval from -3 to 3, and then a linear space where we have basically 100 points. Now let's play around a little bit with the code. Well, first we reproduce everything. Yeah, that looks like before. Now play around with the tolerance. We make the tolerance larger. That means we want to have a less accurate result. Let's make it really large, 0.5. If we're less accurate, we need less points. You see that? So 1, 2, 3, 4, 5 points basically. If we want to have a higher accuracy, we need to have a smaller tolerance. Like when I want to have really smart students, your GPA always should be like, what is a 4 point? Right, something like this. Putting numbers onto things. Of course, it doesn't really work like that with people. Okay, so now we look into the code. What does it do actually? Where are my 3 steps of my bisection method? Because here we start initializing a plot, right? Then we plot our original function with a line width of 0.5. We have a helper line at 0, helper line here, auxiliary line horizontal, just to see where should be the root, right? That is this part here. The x-axis, so to say, shifted our line at 0. We have the labels, and then we define our start and stop values, fa, fb, as function values of f of a and f of b, and we plot those as points. K is black, S is square. K is black, O is circle, right? We go to the plot. Here's the start, black square. And here is the stop, black circle. Very good. So next, root finding algorithm for the algorithm short. Good. So title set. Oh, right. So we have here a while loop. And the while loop runs until the difference between A and B is really small, right? Smaller than the tolerance. And A and B are the positions of my intervals I'm choosing, right? Step 1, choose your interval, A and B. Then step 2, find the middle point. How do I get the middle point? A plus the average of A and B positions. Okay, do you agree? We can have an example. What is the middle between 3 and 5? 3 and 5 is 4, right? If you just take the average, what do you get? No? That's actually the difference divided by half, right? You can also work with the average. So 5 minus 3 is 2, 2 by 2 is 1, 3 plus 1 is 4. Yes? Seems to work. Then we have the value of a function evaluated at m. We call that fm, right? The value, and the evaluation always f of m. Then we plot this as a new point. And the point we put at the position x equal the middle point. The function value will be the just evaluated value, and it should be a red circle. Then we put a text on it saying m, taking an integer here, where the integer is actually the iterator. And we start with the iterator n equal 1. And after that, we increase n by 1. So far, so good. So, and here is now where we decide which interval to take, the one with or without the change of sign. So, what do? We check if the sign, right, if it's plus or minus, of f of a equals the sign of f of m. If it's not like this, then our new values for b, that is the end of our interval, and the function value of b will be m and fm. So this is basically the situation over here, right? So we see that a and b don't have the same sign. What we do is we take the values of b and we rename them as the first interval, which here is labeled c, right? And we repeat then our loop with those new values. If it is outside, we basically change our starting interval with the with the middle values m and fm. Okay, so what do? We actually, sorry, what was that? We can monitor our iteration and the values of fa, fb, and a and b for each iteration. So let's see. Where is it? Oh, we need to reset everything. Yes. Okay. So look here. So we start with 0 and 3. Why is it not minus? Right. We need to take this and put it over here before the if statement, right? To get started. So we start with basically minus 3 and 3. Is it doing something? We need to reset the values. Yes, I forgot again. Right. So every time before we update the interval, we set iteration, the function values in our interval. So we start from minus 3 to 3. So we have here the start as minus 3 and 3. But then our middle value is at 0, and we see that the crossing is somewhere between 0 and 3, right? So in the next iteration, we have updated our starting interval to take the values from 0 to 3. Right? But then we see, hey, the crossing, now the next interval is from 0 to 3. We put the middle value at m2, which is 1.5. But now the interval should be between, or the next interval should be between 0 and 1.5, not between 1.5 and 3. So we see, yes, our implemented bisection method really selects the next interval. Also, what we notice is every time we perform this function call in the while loop, the interval is splitted in size in 2. So from 6 units, we go to 3, to 1.5, to 0.75, until the difference is really, really small. So let's check how big is the difference. We're asking for differences of 0.0005. Now the last interval that is written here is larger than that. But be very, very careful, because we asked to print before the interval is updated, so we could see the first change. If we print the final results only and not each iteration, I need to update again. We actually see that the tolerance has been reached. Right? And how many iterations do we need? 15. Now we know that the function values, yeah, it's very close to 0. And well, the solution here I would give as 0.693 for rounding, right? Okay. Are there any questions to the bisection method? So this is a very, very simple way of finding solution. I think it's, considering its simplicity, it's really nice. We can implement it basically in, well, we did implement it in 1, 2, 3, 6 lines. I think one can do it probably in 4. Right? 4 commands if you do it nicely. Maybe even in, if you really push it, probably in 1. Right? Doing some fancy nested list comprehension. Okay, if there are no questions, then next time we look into Newton's method. Please remember to make sure that you come to the final exam. Because so far, most of you did pretty good. Don't screw this up. Final exam will be twice as much as the midterm. Prepare well, so you can leave comfortably this course. And that's it. Then we have 7 more minutes you can spend on your practice. Right? We have 1, 2, 3 practice.